We're starting off today with Unit 6. And Unit 6 deals with random variables. And I forgot to get logged on with my iPad, so I'll do that real quick. But just keep in mind as I'm doing this, that random variables are always labeled with capital letters. Here we go. So a random variable could be X or Y or B or whatever. You could have S. You get the idea. Capital letters means it's a random variable. A random variable is one that we know the probability distribution for what the values could be, but we don't know exactly which value it takes on. So it can have an average value and then some kind of spread around that, the standard deviation, of course. And that's a random variable. So in association with that, we have expected value. The expected value of a random variable is the mean of it. So I should have done that the other way around, but you get the idea. The expected value of random variable X is the mean of X. And to find the mean of X, we need to have a probability distribution, which is frequently given, maybe in a table where you have like a few values, let's say 1, 2, and 3 are your values it could take on. And there's a 30% chance of this, a 40% chance of this, and then another 30% chance of this outcome. So we can plug those in. And one thing maybe to talk about right now, because it'll come up later, if you want to find the expected value, the easiest thing to do calculation-wise is to create two lists. And in your calculator, you would do a one variable stat for list 1, but list 2 would be your frequency list. So that is where that frequency comes in, only when we're dealing with probability distributions. You could do it by hand by doing 1 times 0.3 plus 2 times 0.4 plus 3 times 0.3. And in something like this, it's not that bad of a calculation. But generally speaking, lists make this a lot easier. The combined random variables. Okay, so we didn't really talk about the spread as much, but the standard deviation will depend on the type of, well, it'll be given. I'm jumping ahead to sampling distributions a little bit. But the standard deviation, if we have two standard deviations, let's say the standard deviation of X and standard deviation of Y, and we want to combine these together, we can't just add these two standard deviations. Instead, the standard deviation of X plus Y is the square root of the variances added together. So square root of X squared is the variance of standard deviation of X, and square root of, the standard deviation squared Y. So I'm not saying it clearly, but there we go. The standard deviation of X squared plus the standard deviation of Y squared, that's the combined variance. And then we can take the square root of that to get the standard deviation of X plus Y combined. And remember, it doesn't matter whether we're adding or subtracting the random variables, we will still combine them, the variances, to get the standard deviation. Okay, so hopefully that came across clear enough in the end. Trying to think if there's anything else worth saying with that, but not too bad. Maybe I can just say that the mean of X plus Y will just be the mean of X plus the mean of Y. So that's pretty straightforward. Bernoulli trials, this is where we get into the other part of this. And that is, now maybe I'm jumping a little bit ahead with Benz and BIFs. Remember, Benz is for binomial and geometric. So let's talk about the binomial distributions, which would be a situation where you're trying to find out how many successes can you get out of n trials. Geometric probability, or geometric distributions, is the number of trials until you get your first success. And Benz means this is the criteria that we have to make sure this meets before we can use binomial distribution. So B has to be binary. It's either a success or a failure. Independent, the outcome of one doesn't affect the other. N is for the set number of trials to determine that it's binomial. and S is the same probability for each trial. All right, so the B, the I, and the S is the same for geometric, but F represents how many trials until we get our first success. Geometric we didn't do as much with, but it is important, and we will see a little bit of it in our review today. All right, just bullet point stuff there. And as we're going through, if you have questions, you can certainly stop me along the way. You can make notes to yourself to come back to this stuff and look at it. All right, so this is a probability distribution that we're looking at, and this is a cumulative probability distribution. So we don't really work with cumulative probability distribution. So I want to convert this not from this, but to the probability of t. What's the probability that this specific outcome will happen? So I can just say, obviously I started at 0, and what I added for 2 was 0.125. So no change here, but now I can see what's the amount of probability that I added. And that is also 0.125. And we'll see every time we go down, we're adding 0.125. So I will go ahead and fill this table in. And what this is showing us is that if we created a histogram to show the probability, it'd really be like a probability function to show what this distribution looks like, we'd see that every single outcome, except for the last one, that one's 0. Every single outcome except the last one right here has the same probability of happening. So it's a uniform distribution. All right, so your friend claims that the distribution is skewed to the right. Well, it's not. So we know that it is uniform. So this one's uniform, everything else we can cross out. All right, so now the question is, what is the mean equal to? And this is where you could just do list 1, or sorry, not there. You could do list 1 with the actual values and list 2 with the frequency, the probability distribution of it. And then you could run your one variable stats to give you your mean. But in this special case, when you have a uniform distribution, these are all equally likely to happen. So we can just do a straight up mean of all of these outcomes. So you can actually calculate this one by hand pretty quickly. And there's 2 ways of doing it. You know that all these center around right here. So 5 and 6, 4 and 7, 3 and 8, we see it's 11 every time. So that's going to be 44 divided by 8 outcomes, which is 5.5. Now, if you understand this concept, and I don't want to confuse anyone, but knowing that it's the same, it centers around the same value, you can also just take the top and bottom value, which is 11, and divide it by 2, and you get the same thing. It varies around the center the same way. I want to point out this quick calculation only works, both this and this. This only works when it's a uniform distribution. So if we had a really strange distribution here, you could not do that. You would need to set up your lists. But anyways, we can see that 5.5 is the mean, and it is greater than 5. So there's our answer. All right. Again, I might be going through some of this stuff quickly. If you need me to stop right where I'm at and ask a question, you can do that. But otherwise, I'm just going to keep zooming through. All right, random variable R is normally distributed. We have the data on that, so the parameters. So variable S is defined by this right here. And keep in mind, this is not combining random variables. This is transforming a random variable. So you could think of this as changing the units. And so we're not fundamentally changing the shape of the distribution or anything. We are just, or maybe I'm not saying that right. We are changing the shape and where it's located, but we're not fundamentally changing what the data is about. We're just changing how it's being expressed, maybe by changing units. So anyways, when we do make this change, we have 2 things we can, when we're dealing with the mean. So the mean of S is going to equal 7 plus 2 times the mean of R, because means can be multiplied and added to or subtracted from. So the mean of S is just going to equal 7 plus 2 times 8, which gives me 23. So I can cross these two out. It's not going to be those. Now I need to find the standard deviation. The standard deviation of S is just going to be 2 times the standard deviation of R, because standard deviations can't be added to, you can only multiply them or divide. And now you get 2 times 21, which is 42. So there's your answer. Okay. So next problem, we are going to look at a binomial setting. All right, and what this means is that we have a set number of trials. So we're going to talk about a baseball player getting 600 trials of at-bats, and 200 is the kind of data point that we're looking at. So how many successes? So we're going to use this, and we'll figure out how we're going to use it exactly. And the probability is 0.28. So if we run through bins just to make sure this is appropriate, it is binary, that he could succeed or fail. It's independent. We're going to assume every at-bat is different and not affected by the last. We have a set number of trials, and the probability is going to stay at 0.28 the whole time. So this is where we have two options. We have binomial PDF, and we have binomial CDF. And remember, PDF is to say, what is the probability that we get exactly X number of successes out of N trials? But we don't really, in this case, we're not worried about getting an exact amount of successes, like, but that could be the case in other problems. We're looking for what is the range of successes that we could have. And we're looking for 200 or more hits, which means 0 to 199 hits represents failure, and 200 plus is success. So with your binomial CDF, this always measures from the left to the right. So we're always going to start at 0 up to whatever your X is of interest. So we can't measure from 200 to beyond. We have to measure from 0 up to. And so in this case, I'm going to get the complement of 1 minus binomial CDF of, and when you go to your distribution screen, so just to make sure these numbers make sense, you want to go to your distribution, go down close to the bottom and open up your binomial CDF. We're going to have 600 trials. The probability each time is 0.28, and X value, the number of successes, is 199 because 200 is considered a success in our larger problem. So up to 199, we're getting the probability of failure. So if I plug those numbers in, I get 1 minus 0.9976, which gives me 0.0024. And of course, we did the complement of that because the probability that this player gets 200 or more hits is only 0.2%. So there's my answer. It would be highly unusual if he got that. All right, 12% of all Dynamite mints are candies are orange, and 60% of all holiday mint candies are orange. 2 independent random samples, each of size 20, are selected, one from Dynamite mint candy, the other from holiday mint candies. The total number of orange candies in the 2 samples is observed. What are the expected total number of orange candies and the standard deviation for the total number of orange candies, respectively, in the 2 samples? So let's figure this out. We first of all want to figure out what is the mean of Dynamite mint plus holiday mints. And to do that, I need to know the mean of Dynamite mints, and I need to know the mean of holiday mints. Okay, and this is where we have some formulas. I forgot to write these out at the beginning, but when you're dealing with a binomial situation like this, and that's what this is, because we're talking about what is the number of successes we would expect out of a sample size of 20. Okay, so the mean for binomial is going to be, I'll just put x right here, it's going to be n times p. And then we have this other formula, which is the standard deviation, which is going to be, let's see, it is square root of n times p times 1 minus p. And I bet a lot of you forgot those formulas. And that's totally fine. If every one of you forgot this, then I'm fine with that, because these are not formulas you need to have memorized. They're in your formula sheet. I'm just reminding you of them right now. But if you go back to your AP formula sheet, you can find where it actually says binomial setting on there, and or binomial distribution. And it tells you the mean of the standard deviation formulas that you need. So just be able to look it up. Okay, so let's get the mean for dynamite mints. I know that I have 20 mints, and the probability is 12%, so 0.12, which gives me 2.4. The mean for holiday mints, I'm still going to have a sample of 20, but now I'm going to have a 60% probability, which gives me 12.4, or sorry, 12, not 12.4. Let's put 12.0. All right, so now, because I have these two means, all I have to do is add them together. So 2.4 plus 12 gives me 14.4. So I've got three options with that as the mean. I need to find the standard deviation. And the standard deviation is a little bit trickier, maybe, or it's just a little bit more math required. And the standard deviation of dynamite plus holiday mints is going to be the square root of the variation of dynamite mints plus the variation of holiday mints. Okay, so I need to just figure out what this is. So the standard deviation of dynamite mints is going to be 20, and I'm using this formula up here. So 20 is the sample size, 0.12 and 0.88. That's the probability and the complement of the probability. I'll go ahead and write the equation out for holiday mints, which is going to be another sample size of 20. This time there's a 0.6 success rate and a 0.4 failure rate. So I'm just going to plug those numbers in and then plug them into this equation down here. Hope you guys do the math as well at home. So I am writing on the screen, but I hope you guys are just kind of glancing up once you complete your calculations just to double check your work. Okay, so if you ran through and you did all the math yourself just to double check your work, there it is, and we can see 2.629 is the outcome of that. All right, so let's move ahead. Random variable x has geometric distribution with p equals 0.37. Approximately how far do the values of w typically vary on average from the mean of the distribution? So this is a geometric distribution. The other formulas that you might need to use on occasion, if you have a geometric mean, a geometric distribution, I mean, the mean of it is going to be 1 over p. Remember, geometric distributions are ones. What's the probability of this particular trial being the first success. So the average point that you're going to get your first success is 1 over p. And the standard deviation in this case is going to be, it's the square root of 1 minus p over p. Geometric does not come up very often, but when it does, you have to be aware of it. So this is asking, and I guess there's a typo here. It should have been x, but not a big deal. How does it vary on average from the mean of the distribution? So basically it's asking for the standard deviation here. So the standard deviation of x is going to be the square root of 1 minus 0.37 over 0.37. And now it's just a really pretty straightforward calculation. I'll go ahead and put the 0.63 right here. And everyone can do that. And you can just circle when you find what the correct answer is. There it is, 2.15. I mean, we could go one step further. We could figure out where the average is going to be. So 1 over, I know it's not asking that, but just to get some practice. So if I did 1 divided by 0.37, it's going to take on average until the 2.7 trial. So if I did this over and over and over and over again, it would average to 2.7 trials until I get my first success with a standard deviation of 2.15. All right. And we didn't really go much further with geometric distributions besides that. Okay, last one for this unit. A die is used in a certain board game, and it has 8 faces. 3 red, 4 yellow, 1 blue. Each is equally likely to land face up. The player tosses die until blue lands face up, and the number of tosses before blue lands face up is counted. What is the probability that a player will toss the die at least 4 times before blue lands face up? So in this case, this is, we're really looking for how do I say this? We don't want the first success, and we're going to call success in this case getting a blue. So the probability of success here is 0.125. That's 1 in 8. So there's 1 blue face on an 8-sided die. So the probability of success, and you have to keep in mind, success doesn't always mean success, because this actually means that we failed at the game and the game is over. But a success is getting that blue. So we don't want to get a blue on the first trial, the second trial, the third, or the fourth, but any after that doesn't matter. It could be the 5th, 6th, 7th, ... These are all fine, but we don't want to get a success here, 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 or here. So we want our first success to be here at the earliest. All right, and that doesn't mean it has to be a success. We could still fail here and then not get our first success until the 10th time, right? But anyways, the way that we want to think about this is if I used a geometric CDF function, then this tells me what is the combined probabilities of all of these being the first successes. And so I could do a geometric CDF to get the combined probability of the first trial being my first success, the second, the third, and the fourth, and then stop there. If I wanted to do a PDF, maybe the problem would be, say, what's the probability that the player will toss the die exactly 4 times before blue lands face up? And then I would be looking at something different. So anyways, this is saying at least 4 times. So if you followed me so far, here's what we want to do. You can go into your geometric CDF, which is the very last function in your distributions menu. The probability here is 0.125. And I want to get the probability up to 4 trials before I get my first success. And what this is going to give me is the probability, the combined probability that I get 1, 2, 3, or 4 is the first trial that I succeed at. So I'll just put 4 in. I can paste that and I get, this is 0.4138. Now this is not what I want to have happen, so I just want to get the complement of it. If I can get the complement of this value, that's going to give me the probability of having the scenario play out like we hope. So 1 minus 0.4138 gives me 0.5862. There's a 58.6% chance that I will last at least until the 5th trial until I get a blue. Okay. Good times all around. Unit 7. Now we're looking at sampling distributions. This was the very last thing that we looked at before the end of first semester. And it really helped set up, I will say it was kind of a weird time, and maybe there was some content in there that was a little bit maybe forgotten and lost in the hustle and bustle of everything else. But sampling distributions really help set up all of the hypothesis testing and confidence intervals that we do later. Okay, this doesn't read exactly the right way, but if you imagine all of the samples of size n that could be drawn from a population, then what they would do is they would all center around a mean. And you can ignore the writing, I kind of made a mess of that. But you're going to have a bunch of different possible samples of size n, and you'll get a sample mean or proportion from that. And they are going to fit around the true population parameter and in a normal distribution. So what if you're going for means, you're going to have a true mean. If it's proportions, you're going to have a true proportion that everything centers around, because this is another thing in here is it's an unbiased estimator. Okay, so that came up. Now the spread of this distribution will change based on some factors, and that's going to be part of what we talk about with this. But that was the main idea. In fact, moving forward, when we get to hypothesis testing, everything that we're doing is comparing the sample result we got to a sampling distribution from a population. We weren't comparing to populations, but to a sampling distribution. And so that's why the formulas that we're going to be using here look very, very familiar to the ones that we were using for all of our tests. All right, so if that concept never clicked for you, hopefully as you go through it, you can maybe draw that connection. The center of that distribution will be an unbiased estimator of the true population mean or proportion. So I did already talk about that. The spread is one of the main new pieces of information, and that, like I said, is what we carried forward. So the standard deviation for X bar, which would be a sampling distribution of sample means, that is going to be the true population standard deviation divided by the square root of n. And that hopefully looks familiar to you. All right, the standard deviation for p hat, which would be the sampling distributions of sample proportions, is going to be the square root of p times 1 minus p all over n. And again, that should look very familiar because you've used that formula quite a bit, but it was introduced here. Now with this unit, we were always assuming that we knew the true population parameters. And so moving forward, we didn't know that, so we used p hat to estimate it. That's why we call it standard error. Okay, let's move forward and kind of do some practice with this. The continuous random variable R has a mean of 12 and a standard deviation of 2.4. What is the probability that R equals 10? And this is kind of a minor conceptual point, but we did talk about it. The probability of any specific outcome in a continuous random variable is always going to be 0. We never look for a specific outcome. What we look for is a range of outcomes, like greater than or less than or between two values. And you're quite familiar with that. All right, a tire manufacturer calibrates the manufacturing process to produce tires that have a mean tread thickness of 20 millimeters and standard deviation of 0.8 millimeters. Of the following, which is the least thickness of a tire in the top 20% of the distribution? So this could have very well been a problem right off of unit 2 with the normal distribution, because essentially they're trying to say, hey, what's the z-score that we need, and what x value do we need? If I can draw that in. So we're just working with that. This is straight from unit 2. All right, so we know the mean is going to be 20. We know the standard deviation is 0.8. We don't know the actual value for x. And what we need to do is figure out what does the z value have to be the top 20%. So if it's the top 20% that we want, that means we're at the 80th percentile. So on these calculators from school, we only can measure from the left. Some of you have the TI Inspires that can measure a right tail. But what we want to do here is inverse norm. And we had practice with this the other day. I want to get the area of 0.8 under the standardized normal distribution, standardized normal model. And when I do inverse norm of 0.8 area, I get 0.8416. All right, so now I can do the algebra, figure out which x value will give me the z value of the z-score of that exactly. So anyways, I'm just going to do the algebra without showing it on screen. Okay, 20.67 millimeters. Now, we do not have that as an answer choice. So the question is, which of the following, which is the least thickness of a tire in the top 20%? So anything below this value right here is not in the top 20%. 20.2 is not above that value. 20.6 is not above that value. So now the question is, which is the least thickness of the ones provided? So we're looking for the lowest value that's still in the top 20%, and it's right here, 20.8. Okay, 2 simulations will be conducted. We've got 500 trials and a sample size of 125. We've got 750 trials with a sample size of 100. So this is where we want to remember that the standard deviation is always inversely related to the sample size. So the bigger your sample size, the smaller your standard deviation. And therefore, if you had a distribution that looked like that and you raised the sample size, well, it would be a lot narrower. I'm giving very extreme examples here. So because simulation 1 has a bigger sample size, I'm going to just show this as being sample 1, and this is simulation 1 and simulation 2. Now, it's not that extreme of a difference, and you guys probably realize that, but it's just to help illustrate. So these are both going to be sufficiently big to be unbiased estimators of the true mean. So the means for these should not be any different. This is both going to be the true population proportion that it centers around. So the center will be the same. So that crosses off these. Well, it doesn't cross off this one, but we know the variability is different. So the variability is not the same. So I'm crossing that off as well. And we know that simulation 1 is going to have a smaller standard deviation, so therefore it has less variability than simulation 2. And there's my answer. Okay, same kind of question going on here, just a little bit of different nuance added in. So what is going to produce the smallest standard deviation for the sampling distribution of a sample proportion p hat? And here I kind of want to bring up this formula, which is square root of p times 1 minus p divided by n. So anything in the numerator is directly proportional to the standard deviation. Anything in the denominator is inversely related, inversely proportional. So the bigger n is, the better. I'm going to cross these three off. Now the question is it better to have a p close to 0.5 or closer to 0.1 if you're trying to get as small of a standard error as possible? And if you don't know, and this isn't something you have to keep in mind, we can just pick two values. So 0.5 is right at 0.5. I'm going to use that for one of them. 0.1 is much closer to, all right, I'll do 0.9, I'm sorry. 0.9 is much closer to 1. So I can just compare those two. So I'm just going to worry about the numerator part of this. P times 1 minus p whenever it's 0.5. That gives me 0.25. So if it was 0.5, I would have 0.25 in the numerator. All right. Now, if it was 0.9, it'd be 0.9 times 0.1, which is 0.09. So it seems the closer I get to 1, the smaller this value is, the smaller our numerator is. And because I want a small standard deviation, as my proportion, my population proportion, as this goes down, my standard deviation, or p hat, is going to go down. So I want the smallest, or maybe saying down isn't the best thing, but I'm going to say further away from 0. So away from 0.5. I can't talk correctly, and I apologize. Away from 0.5. Hopefully this is clear enough. I know I didn't say it clearly. The further we get from 0.5, the smaller our standard deviation is. So this is my best outcome right here. All right, I'll pause there. Were there questions on that? Okay. According to data from the U.S. Election Project, only 40% of eligible voters voted in 2018 elections. For random samples of size 50, which of the following best describes the sampling distribution of p hat, the sample proportion of people who voted in the 2018 election? All right. So in this case, they're asking us to figure out, is our sampling distribution approximately normal? And what does this mean the standard deviation going to be? The way we assess normality is with large counts. That means n times p has to be greater than or equal to 10. N times 1 minus p has to be greater than or equal to 10. And I know that p right here is 0.4. Sample size is 50. So when I do 50 times 0.4, I get 20. That's greater than 10. 50 times 1 minus p, which is 0.6, gives me 30. That's greater than or equal to 10. So it should be approximately normal. It is not going to be skewed right. The mean of this sampling distribution for proportions, so just put mean for p hat, is going to be the same as the population proportion. So in this case, the mean here is going to be 0.4, because that's what it tells me. So this doesn't really help because all of them show 0.4. But now the standard deviation for a sampling distribution for sample proportions is p minus 1 times 1 minus p divided by n. And I can do this calculation pretty quickly. So p is 0.4, 1 minus p is 0.6, sample size is 50, and now this will finally tell us what our answer is. 0.4 times 0.6 divided by 50, and I got 0.069. So it was a little bit off. I don't know why it showed 0.068 instead of 0.069, but that is our best answer. All right, the last question we're going to go through today. A researcher conducted a random sample of stuff and wanted to find things. And it looks like we've got population mean. So I'm just going to put this up here. The population mean is 1,850. The population standard deviation is 315. We are dealing with a sampling distribution. So the mean stays the same, but my standard deviation for X bar, the sampling distribution of sample means, is going to be the square root of, sorry, it's 315. Well, let me write it this way first of all. It's going to be the population standard deviation divided by the square root of n. So that's 315 divided by the square root of 100. And that's pretty quick math because we know the square root of 100 is 10. Divided by 10, it's 31.5. So even though the population has a distribution that looks like that, the sampling distribution is going to look like this because when we take a bunch of samples, we would expect this sample means to be closer to the true mean than individual values would. Okay. So now we can figure this out. This is essentially just one more normal CDF calculation. We have a sample mean of 1,920. How likely is it to get that sample mean or greater? Well, we can figure that out. I can find the z-score of that, which is 1,920, which is our actual value, minus the mean, which is 1,850, divided by the standard deviation. Here's the sampling distribution standard deviation. All right, we'll just go through the whole problem. You could probably do it from here, but why not? So when I found the z-score, I got 2.22. And everyone should be able to find that. So now it's just going to say this sampling distribution, or this actual sample was way over here, you know. So what's the probability of getting that or higher? That's just a normal CDF. So I don't think I will do that calculation. I know we got right up to the end and I'm just not going to finish it. Am I the only one who's bugged by that? Okay. I'm kind of OCD. I'm going to go ahead and do it because I hate not finishing. All right, the normal CDF tells me that there's only a 0.013 probability of that happening. So there's your answer. All right, so if any of this did not make sense, you can certainly stick around, ask questions. Your homework is 2 more FRQs. We're going to go through the 5, 6, and 7 FRQs tomorrow in class. Just a brief discussion that I'll guide for you. And we're going to look at units 8 and 9. So anyways, if you are good to go for the day, have a wonderful day, and I will see you tomorrow. Otherwise, stick around and I'll answer any questions you have.